All right, good day, scholars. Welcome to today's class. In today's MTH202 class, I want to focus on call of a particular field. And don't forget that you've been told or you've been taught before now that whenever we are finding the call of any field, it has to be a vector field. You find the call of a vector field to produce a vector field. So whenever I take a vector field and I find the call of it, the answer must be a vector field. Unlike divergence, where you find the divergence of a particular vector field and it will produce scalar. But for call, you find the call of a vector field and it must produce a vector field. So take for example, if I have this field F, this is a vector field F, and it's written as Fxi plus Fyj plus Fzk. That means I'm in a Cartesian coordinate system. Don't forget that Cartesian coordinate system. This is a Cartesian coordinate system, IJK, and you see the XYZ component. So in this case, if I'm to find the call of this particular vector field, call means cross product. And how do we find cross product? By definition, our nabla is defined as partial x, partial y, partial z. That's your nabla. And you want to cross it with your f, which is defined as fx, fy, fz. So don't forget that we can write vector in this bracketed form or in this form. You can write it like this or you write vector like this. So how do I find the call of this individual? I use the determinant form. So I have my I component, the j component, and the k component. So I have partial x, partial y, partial z. Then I write the other one. F with respect to x, with respect to y, with respect to z. Then we go ahead and we take the determinant. This is just like a remembrance to what you've been taught before. Then we take the matrix, the determinant of this whole thing to get our final answer. So we concluded that whenever I find the call of a particular field and my answer is 0, don't forget the call of this field f cannot produce this kind of 0. It has to be a 0 vector. Because I told you that the call of any vector field must produce a vector. So once our answer is 0, we say it is irrotational. But once our answer is not 0, we say it is rotational. That means there is a rotation involved in that field. But today's class, I want to focus on, I only picked Cartesian coordinate system to show you something that happens here. Now let us switch to orthogonal coordinate system. That's my major concern for this part of the tutorial video, orthogonal coordinate system. So let's take this and let's change our f from the XYZ down to another field, which is the orthogonal part. And in the orthogonal part, I told you we have the spherical coordinate system and we have the cylindrical coordinate system. So in an orthogonal system, let's say we have orthogonal coordinate system. In an orthogonal coordinate system, let's say we have u, v, w, an arbitrary orthogonal coordinate system. If I want to assume a particular vector field f, then I should have f, u, eu. Don't forget that the unit vector has now changed from be your ijk to eu, ev, ew. Here also I should have f, v, ev, and fz, fw, ew. So, and we call our EU, EV, EW all together. We say they are what? They are bases, or we call them base vectors. So they form base vectors, but each of them we call them unit tangent vectors. Don't forget that EU is a tangent vector. When I write this EU, this is a tangent vector. Tangent vector. When I write EU with the cap, it becomes a unit tangent vector. Right? A unit tangent vector. When I write them together in the set form, the three of them will form bases or base vectors. So now moving to what I really want to show you today. So how do I now find the call of this particular guy, which is called of f in an orthogonal coordinate system? So in an orthogonal coordinate system, the definition for my nabla should also change, such that I now have partial u. It has switched from xyz component to uvw. So I should have partial u. That's for my nabla now. Here I should have partial v, and I should have partial w, right? And you also want to cross it with fu, eu. Let's write this in bracketed form: fu, fv, fw. So this should be what I should write, right? From the Cartesian coordinate system I explained. This should also be what you think I should write. But no, in orthogonal coordinate system, when I taught you the divergence, the formula for divergence in orthogonal coordinate system is different from what you have in Cartesian coordinate system. So similarly, the formula for my call under orthogonal coordinate system should adjust and should be something entirely new. So I'm saying this thing is not correct. You can't have the call of a vector field in orthogonal coordinate system as this guy. So what should it now be? Now let me write and let me show you what the new system should look like. A moment, please. Because at the end of this class, I'll be giving you an example and a question to solve. So I'll give you an example and a question, and once I'm done with the example, I'm very sure you will get the question that I want to give to you. So what should be the new formula in my orthogonal coordinate system for my call? Then the formula changes and I have 1 over hu, hv, hw. Then you have your hu, eu component, hv, ev component, hw, ew component. Then you have partial u, partial v, partial w. Also, I have hu, fu, hv, fv, hw, fw. See this, unlike my Cartesian coordinate system, where I just have my ijk and I have my partial x, partial y, partial z, fx, fy, fz. Here, our scale factors must be added to each of them. Don't forget that I told you in Cartesian coordinate system, each of the vectors, you have your target vectors, they are what? Unit vectors. That means the magnitude is 1. But unlike this place in orthogonal coordinate system, each of the coordinate system you're considering, whether you're considering spherical or you're considering cylindrical, their hu, which is now called scale factors, differ. So orthogonal coordinate systems, they don't have a general scale factors. Their scale factor switches according to what type of coordinate system you are engaging. Unlike Cartesian coordinate system, where it's just general for all of them. So this will be your formula, your new formula now in orthogonal coordinate system, a general formula. So now let's now break it down, and from this same thing, let's generalize and let's bring for, let's take cylindrical first. Cylindrical. So for cylindrical coordinate system, where we'll be having rho, theta, z. And I said some textbooks might decide to use r, theta, z instead of rho, theta, z, which is still okay. So in this case, now alright, so in cylindrical coordinate system, where I now have rho, theta, z, let's check together. Our f now becomes f, which will now be f rho, e rho, right, plus, I'm still following what you have here. You know, this is general. UVW is for general orthogonal coordinate system. Now, I'm picking a particular type, which is cylindrical. So, for the other one, I have F theta, E theta, and I have FZ, EZ. Are you following? FZ, EZ. So, what should now be my HU, my scale factors? In cylindrical coordinate system, my scale factors, H rho should be what? 1. I like your energy. My H theta should be what? Should be rho. And my HZ should be 1. That's good. You're following? So what should now be, where I'm going is actually the formula for the call of this guy. So permit me, I will be changing what I have here and you'll be following me and be telling me what the response should be. So for this, I've changed this. We are no longer here. We are now in Cartesian coordinate system. In Cartesian coordinate system. So the new one compared to what you have here, which will now be curl of my f. The curl of my f should now be 1 over hu, which is now h rho. I should have 1 over h rho, h theta, hz. Then instead of hu, I have what? H rho, e rho, h theta, e theta, and hz, ez. Also, I have partial rho, partial theta, partial z. And finally, I have h rho, f rho, h theta, f theta, hz, fz. What do you notice between this and this? This is general. This is now specific formula for each of them. Cylindrical coordinate system. If I'm in spherical coordinate system, I won't be having rho theta z. I'll be having rho theta phi. You should be familiar with that by now. So we are cleaning this now because I'm no longer here. This general one. I'm now in cylindrical coordinate system. So we have to rub this off. So in cylindrical coordinate system rather, what I will now have will be 1 over, what's my h rho? 1. H theta, rho, hz, 1. When I multiply, because multiplication is what is connecting them. When I multiply 1 rho and 1 together, I should have what? Rho. Then I have as well, what is my h rho? 1. 1 times e rho. I will still have e rho. What is my h theta? Rho. Then here I have rho e theta. And what is my hz? 1. Then this should be ez. And at the other end, I have partial rho, partial theta, partial z. Did you notice that wherever rho is rho all through, theta all through, z all through. Don't make the mistake. And here as well, h rho, whatever you have here, that's what is replaced here. Can you see that now? So h rho also should be 1 times, I should have f rho, I should have rho f theta, and I should have my hz also is 1, then I should have fz. So this becomes the formula for curl of a vector field in cylindrical coordinate system. So if I'm going to spherical coordinate system, what will change there? What will differentiate them? The scale factors. That's why your scale factors must be the most important thing you want to master. Let me even test your knowledge. In scale factor, what's your h rho? I'm not telling you, you tell me that in your notes. What's h rho in spherical coordinate system? What's h theta and what will be h phi? So you write that down in your notes. I will check. Okay, so let's take an example so that I will be sure that you've gotten what I've just explained. Let's take an example from my notes. Example. These questions here ask us to find the curl. It says calculate the curl of, we have theta e rho in the cylindrical. So they said in the cylindrical coordinate system. In the cylindrical coordinate system, rho theta z. So we want to find the curl of this. This is a vector field, right? E rho. That means if I want to write this vector field they've given me, I can say this theta e rho is the same thing as having, for the rho component we have theta e rho, plus for the theta component we have 0 e theta, right? And for the z component is also 0. Do you understand what I've just said now? This single thing is in 3 components, rho theta z. But for the, it only has the rho component, which is this. Every other ones are 0. I'm intentionally writing this so that you can be familiar with what is happening here. So now let's solve. Solution to the question we have using the formula. All you just need is this formula, the one here. Let me mark it. This is what I want to use, the formula for curl. So according to the question now, our f is what? Theta E rho. That's our F. So if I want to find the call of theta E rho, the call according to the formula theta of this, so that should be 1 over rho, right? Then I have E rho, I have rho E theta, and I have Ez. At this other region, I have partial rho, partial theta, partial z. Lastly, my F rho. Now, the F that I have, the feed, only has rho component. So my F rho is what? Theta. My E component, theta component is what? 0. My Z component is also 0. But you should question that, but here is rho F theta. Since our F theta is 0, rho multiplying 0 must also turn to be 0. Do you understand that now? Rho times 0 should be 0. That's why I'm having 0 here. And what you have here is just 1, H rho F rho rather, which is 1 times this, which is also theta. So how do we solve this? Using matrix form. So let me demarcate this. So I have, from my matrix now, I have 1 over rho, which is constant. Then let's open a big bracket. In opening a big bracket, how do we solve this matrix? We put plus, minus, and plus. So for the E rho, we write E rho. What happens at the E rho? I will block this, and I will block this. Then I'll be having partial theta with respect to 0. So that's partial theta of 0 E rho E. Okay, so if I want to find the matrices here, the determinants here, I have 1 over rho. So you open a big bracket. Don't forget that you can't find the determinant of this matrix except you reduce it to a 2 by 2 matrix. That's how you solve. Even if you have a 4 by 4 matrix, you look for a way to reduce it to 3 by 3, then 2 by 2 before you find the determinant. So same thing here. We are working on E rho first. So for E rho, I am blocking this and I'm blocking this. So I only have these 4 components left. So I'm differentiating this with respect to 0. Then I should have partial theta with respect to 0 minus differentiating this with respect to 0, partial z with respect to 0. So we are done with the first part. For the second part, I have minus rho E theta. I'm here now. So because minus is here, that's why minus is here. Then I'm blocking this part and I'm also blocking this part. What will I have left? 1, 2, 3, 4. So if I'm solving this as well, I take the derivative of this guy with this. So that's partial rho of 0 minus, I take the derivative of theta with respect to this. So I have partial z of theta. That's for that part. Then the third part, which is also plus Ez, then I should have plus Ez. What will happen here? If I block this and I block this, I should have 1, 2, 3, 4. So I should have partial rho of 0 minus partial theta of theta, right? Of theta. So we close the big bracket. So I've written for the first, the second, the third. The first one, the second one, the third one. So now let's take the derivative. So this is the same thing as now finding 1 over rho. So I have E rho for the first component. So if I'm finding derivative of theta with respect to 0, that is 0, minus derivative of z with respect to 0 with respect to z, 0. I have minus rho E theta, derivative of 0 with respect to rho also becomes 0. Derivative of theta with respect to z also becomes 0. So everything is reducing to 0. Then I have plus Ez. So derivative of 0 with respect to rho, that's also 0. And derivative of theta with respect to theta, that becomes 1. So that's the only one that has value. So if we work on this, I should have 1 over rho. So for the E rho, 0 minus 0, that's 0. 0 multiplying E rho, that's 0. If I have, for the first part, permits me to use this cancellation, everything here becomes 0. 0 minus 0 also here, everything becomes 0. So which one will I have left? 0 minus 1. 0 minus 1 is what? Minus 1. Minus 1 times EZ. That would be E minus EZ. So what should be my final answer? My final answer is now minus 1 over rho EZ. So the call now, there is a rotation, because I didn't mean our final answer is 0. We say it is irrotational. But with this final answer we've gotten, the original field they gave us was in rho coordinates. Now our final answer, after performing call on it, is now in what? Z component. That's the beauty of call, that we are checking whether the field is rotating or the field is not rotating. So having done this for you, let me give you an example that you'll be submitting to me when I see you or in the next class. So let's take this as an assignment that you will be doing. Just follow what I've explained to you, and I'll be ready to receive any question when you watch this tutorial video. So permit me to pick from my note as well a particular example. So you're doing this yourself, and I want to see the solution. So we are still on call. So this particular question asks us to, so you are doing this yourself. Do it yourself. It says calculate the call of rho E theta. So now they are giving us the theta component, rho E theta in the cylindrical coordinate system. And what's that system? Rho theta z. So I want you to find the call of this one. So we are still under cylindrical coordinate system. In our next video, we'll be moving to the spherical coordinate system. But I want to challenge you to also just try, based on everything I've explained, check for me what spherical coordinate system will look like, so that we can interact together in the next class. Thank you very much.